Welcome to today's session. So we will continue ahead with some revision of mechanics today. Today we will concentrate mostly on the part of the conservation principles, that is things where momentum conservation happens, both linear and angular, and along with that maybe conservation of energy, conservation of mechanical energy, etc. And few questions here and there to do with constraint relations, etc. So I'm not going to stick to any particular chapter like collisions or work by energy or something like that, but rather look at things where the combination of all these concepts come in. But before starting on that part, a couple of questions I want to discuss from the previous. One is from the previous lecture to do with that question I was doing towards the end, where because of loss of connectivity last time I could not complete that question, the approach and separation velocity application question. So I had sent it the solution in the notes to you, but a couple of students have requested to just explain the solution. So I'm just going to go ahead with that firstly. Okay. Okay, so that question was something like this, that initially we had these two particles which were at a distance d and their velocities are like this. Let's say this is particle B, which is going at a velocity u at an angle beta with respect to this line AB, and this is going at a velocity v, and this distance is d, and this is the situation at t equal to 0. Now A's velocity always points at B, okay, and its magnitude is constant, whereas B's velocity itself is constant. So its both magnitude and direction is constant, okay, and V is greater than U. So we have to find time of collision between the two of them. Okay. So as I had explained last time, that if you see the progression of this situation or the system with respect to time, how that is going to happen is, this is the situation at t equal to 0. Okay. Now after some time, let's say at time t, B has reached here and is continuing with the speed u along this direction. But what is happening to A? A is continuously chasing B. So A's direction of motion is changing like this. And at this time t, A might be somewhere here. Okay. And its velocity V is now pointing in this direction. Okay. So it just so happens that my angle looks like 90 degrees here, but let's take it as a variable. Okay. Let's just take it as if this theta is slightly acute. This u is like this, this angle theta is like this. So you can see that at this particular instant, the approach velocity of A towards B, that is V minus u cos theta, where theta is instantaneous. So it is changing with time. So the integration of this approach velocity over time t equal to 0 to t equal to whatever time they collide at. So finally, let's say they collide somewhere here. So A and B reach here at some time capital T, which we want to find out. So from 0 to that particular time, if we integrate this should change the distance between them from the initial distance, which was d, to the final distance, which is c. So we have integration of v minus u cos theta dt from 0 to t is equal to actually we modulus of this thing, because this is how much it is approached in that direction. So this will become d. So we can write it like this, that Vt minus u into integration of cos theta dt from 0 to t is equal to d. This is our first equation. So we can write this equation like this, that Vt minus u into some unknown quantity x is d, where this unknown quantity x is integration of cos theta from 0 to t, which as of now is an unknown quantity because theta is instantaneous. Now on the other hand, we can do one more thing in this diagram, and that thing is that the other thing we can do with this diagram is that, once again, if we are looking at the motion of B, now the direction of motion of B, suppose we take that as our one of our axes in our coordinate frame. So let's take that as our y-axis. Okay. So the perpendicular direction to this becomes our x-axis. So this is our x-axis. Okay. So finally at time t, they are colliding somewhere here. Okay. So we can also see that at that intermediate time, when A was, let's say, somewhere here and B was somewhere here, okay, so if this angle was theta, then over here this line is parallel to the y-axis and this line is parallel to the x-axis. So we can see that this angle theta is going to give us the y component of A's velocity, instantaneous at t equal to t. That is nothing but v cos theta. So therefore, integration of Vy with respect to dt is nothing but the y component of A's displacement. So v cos theta dt integrated from 0 to t is delta y for A. Okay, so that shows us that v into integration of cos theta is delta ya. So we can pick this as our second equation, and we can write it like this, that v into that unknown quantity x is equal to delta y of t. Okay. Now on the other hand, if you compare, now A was over here at t equal to 0. So from here to here, from the initial to capital T, how much A has traveled along the y-axis? This is the total displacement of A. Okay. So the y component of that displacement is this one, delta y. Okay. And in that same time, how much B has traveled? B has traveled this total distance. This is delta y of B. This is actually displacement of B only, which is u into t. So the difference between those two, you can see, is over here how much? B cos beta. So we can see from the diagram that YA is equal to YB or delta YB minus D cos beta. That's correct, Nisha. Yeah. So इसका जो displacement है delta YA, that is equal to displacement of B altogether, which is UT minus D cos beta. So this is like our third equation. Okay. So this is how we can connect these things. So from this and this, we can write that Vx is equal to ut minus d cos beta, and from equation 1, which we had written earlier, we have got this, that Vt minus ux is equal to d. So now we can eliminate x between these equations. So from this we can substitute x, for example, as Vt minus d by u. Okay. And substitute that in this equation. So you get v into Vt minus d by u is equal to ut minus d cos beta, something like this. So v square plus u square, sorry, v square minus u square, my mistake. V square minus u square by u into capital T will become v by u minus cos beta into d. So this time should become and you can see in this if beta was 90 degrees, there's that problem from Irodov that we've done earlier probably, that the time becomes this much. Whereas if beta is equal to 0, then it is a case where they are both approaching each other. Okay, so in that case, the time becomes d upon v plus u. It's a 1D motion. So this equation nicely fits in both these. Okay, so anyhow, so just go through the solution in detail later. So it's basically that trick that you can integrate approach velocity with the instantaneous theta, and you will get integration of cos theta dt as an unknown. And then you can also integrate the y component of A's velocity, and in that again you will get cos theta dt as an unknown. So you can eliminate that unknown. Okay, so just go through this once if you require, then we'll move on to another question. Okay, now let's come back to constraint relations and some applications of them in work energy. So this is very good question to demonstrate this concept, and it is from previous year IIT questions. Okay, so the question is like this. So I'm sure many of you have seen this question before, so I'm going to go through this pretty fast. So this is the initial situation. We have a light thread just going around a pulley now like this. Now the pulley is, let's say, fixed to some wall or ceiling like this, and the other part of the thread. Now one thing interesting you will understand here, that on this block B, no matter how much force we apply downwards, we can never keep this thread straight like this. If we are keeping the thread straight initially, That means we must be applying some supportive force like this. Okay. Anyhow, that question doesn't go into all this. It just says that this is the initial state of the system when we are releasing it at rest. This one has a mass capital M and this one has a mass small m. Okay. Also, the frictionless pulley is at a distance of 2 meters. So this distance is 2 meters. Okay. And capital M is 2 kgs. Small m is half a kilogram. Okay. And also this length here, the thread attached to the wall at this point, this is 1 meter. So that obviously means that this is another 1 meter. We'll ignore the size of the block. Okay. And G is equal to 9.8 meters per second square. So the system is released from rest from this position. Okay, so as I told you, if you want to release it from rest, initially you would have to be supporting the block A. There's no way the tension in the thread can support the weight of the block A because the tension is obviously acting horizontally. So that is something to be understood intrinsically over here. So anyway, so system is released from rest. You have to find speeds of A and B at the instant when A is about to hit the wall. Is about to hit the wall. So you can say just hits the wall. So this is another question where your application of constraint relation is tested nicely. So let us just look at this situation with respect to the situation when it's going to hit the wall. Okay, so when this is going to hit the wall, okay, so at that moment, now this block is here. This thread joining it is here. And this thread has become like this. Okay. So obviously this block has moved up somewhere here. So you can see this will be the displacement of B. Okay. Whereas A has just about reached here. And A is having some velocity BA. And B is having some velocity BB. Okay. So first of all, how can we calculate the displacement of B? A, we can see it has come down by 1 meter because this was 1 meter. So A has made a displacement of 1 meter downwards. So actually A has come by a circular path like this. Okay. So A is describing a circle about this point. So B's displacement we will get, yes, we will get it by the constraint relation, that thread length. Okay. So if this length was 1 meter, okay, now you can see this length here is how much? This length is this triangle's hypotenuse. So it is square root of 1 plus 4. So it is root 5. So B's displacement is root 5 minus 1 meters vertically upwards. Whereas A's displacement is 1 meter vertically downwards. Okay, that's one thing. So next we will apply the conservation of mechanical energy. So change in kinetic energy of A plus B as a system plus change in gravitational potential energy of A plus B as a system should be 0. So half capital M V A square plus half small m VB square minus capital M G S A plus small m G S B should be equal to 0. So we have this relation half 2 into VA square plus half 0.5 into VB square is equal to 2g into 1 minus 0.5g into this factor, root 5 minus 1. Okay. So VA square plus VB square by 4 is equal to G into 2 minus root 5 minus 1 by 2. So this is our first equation, which is coming from conservation of mechanical energy. Now the second thing, the constraint relation. No, not minus 2 beta. Because see the thread that is connecting A and B, no? that one, see how that is going. See Ganesh. So this is quite important here. It's quite tricky. So I'll just label the thread with a different color, then it will become clear to you. Okay. So this thread was like this, no? Okay. So this thread length is constant, no? So this is 1 meter plus whatever, let's say D. Okay, good. Okay. So I'm just illustrating for the others also. So ये अभी ऐसा चला गया. So it's reached here. It's about to hit this wall. Okay. But it's pulled this thread into this kind of situation now. Okay. So this length has increased to root 5 meters. So this will become such that D minus SB plus root 5, that is equal to the original length, which is 1 plus D. Okay. So this is the important. Okay, now in the same diagram, let's illustrate the virtual power concept, okay, which we can also illustrate, by the way, with this thing. Tension T is acting like this over here, where if this angle is theta, that's the same as this angle theta, and tension T is acting like this. So we can see that this velocity vector is along this line. So net power delivered by tension should be 0. So virtual power. So tension is not delivering any power at the pulley. So power delivered by tension at A plus power delivered by tension at B should be 0. So minus TVA cos theta plus TVB should be 0. So VB should be equal to VA cos theta. In this case, it means that VB should be equal to VA into cos theta. From the diagram you can see is 2 by root 5. So that becomes our second equation, constraint relation. Okay. So you can also do this constraint relation thing this way, that if you take this point as a fixed point P, then separation velocity of A from P should be equal to approach velocity of B towards P. So you can see that point P is like this, that point A is like this, and A is going with a velocity VA like this. So once again, this angle is theta. So this separation velocity thing is VA cos theta. And similarly, the particle B is going up like this. So this is directly VB. So there's another way we can understand this. Okay. Now all you have to do is solve these two equations. So here you substitute this. So you get VA square plus 1 by 4 into 4 by 5 VA square becomes equal to 9.8 into 2 minus root 5 by 2 plus half. Like this becomes, and from that we can calculate the value. Okay, so another interesting application of constraint relation, virtual power, and all this. Okay. Next, I want to move on today to some, first of all, some direct application of work by energy type of questions. So this is a very easy and common type of question, but often I see people making mistakes in questions like this. So this is a rough surface which has coefficient of friction 0.2. Okay, and this is the block B, which is of 2 kg mass. This is the block A, which is of 3 kg mass. This spring has spring constant, let's say 10 Newton per centimeter. Okay. Now initially x naught is 0 for the spring. Okay. And the system is at rest. Okay. Now constant horizontal force F starts acting on B. Okay. Find the minimum value of F. So that A is disturbed from equilibrium. Okay, take G as 10 meters per second square. Okay, Ganesh, I'll verify the answer. This is the kind of answer you should get. So in this case, it is 0.2 into 2 plus 3 by 2 into 10. 7 newtons. Yeah, check. Yes, Somadev, your answer is correct. Okay, now the thing you have to be very careful about in this question is the condition, limiting condition for A to get disturbed. Okay. So when is A experiencing the maximum spring force? It is not when B comes to equilibrium. Rather the other way, it's when B comes to rest So if you assume A is not moving, then when has A got the maximum tendency to move? It's when B has reached the maximum displacement or the spring is having maximum extension. So you can approach the question that way, that suppose A is not moving, then what is the maximum spring force it is experiencing? So at the instant when it experiences that maximum spring force, if it just about has a tendency to move, then we have reached the limiting condition. So that is the concept we have to apply over here. So basically it is like this, that if A just about tends to get disturbed, okay, that means that the spring force on A has the maximum value of mu into MA into G. When the spring force reaches its maximum, at that instant, it's equal to the limiting friction on E. Okay. So as you know, assume A is at rest. Initially B is also at rest. X naught is 0. Okay. And we start applying this force F. So after some time, if A is still at rest, okay, but now under the action of the force, B has developed some velocity V. So at that point of time, you can see that the spring force acting is like this. The friction acting is like this because it's kinetic friction. And on this, there is static friction. So first of all, you can see that F into X minus this is equal to half mv square plus half kx square. So this is your application of work energy. Work done by the external force plus work done by non-conservative force is change in kinetic energy plus change in potential energy for the system. That is E plus B plus the spring as a system. You have this. Okay, so you have like this. This kind of thing. Assuming this relation is assuming A does not move. Okay, so you can see that your kinetic energy of B as a function of its displacement is this kind of a thing. It's a parabolic thing. Okay, one root is 0 and the other root is x maximum. Whereas at half of x maximum, it has the maximum kinetic energy. Okay, but this is assuming A does not move. So you can see that x maximum will be equal to 2 times F minus mu mg for B divided by K. That's the second root of this. Okay. So if A does not move, this is the maximum extension. Now, assuming A is not moved, you can see for A to be at rest, the static friction on A is equal to Kx. So that means the maximum static friction acting on A is equal to this, which is equal to 2 times F minus mu mg of B. So this thing should be less than equal to mu mag for A not to move. Okay. Or it should become if it has become more than this, then A moves. So that's the thing. So from here you can see that if Kx max becomes greater than this, then A cannot have been at equilibrium. It would have moved before this situation is reached. So there you are. So 2 times F minus friction on B, kinetic friction on B, should be greater than limiting friction on A. This is the condition for A to be disturbed. Whereas if we make it less than equal to, is the opposite condition. Okay, so yeah, that's why I said that this is a question that once you understand the solution, it's pretty obvious, but there's always a tendency to make a mistake in this question if you're doing this type of thing after a long time. Okay. Now, another application of this time, not only conservation of, not only work energy we can use, we can also use impulse momentum concept or a bit of center of mass type of concept. So this time it's a smooth surface. Okay. Now there are 3 parts of this question. So this system is at rest and x naught is equal to 0 for the spring initially. Okay. It's a smooth surface. So the first part, if a sharp impulse of F delta T equal to M1 V naught acts on M1 initially. Okay. So this kind of a sharp impulse acts on this one. Then we have to find maximum compression of the spring, and let's do this parametrically, and maximum speed of M2. Okay. And the second part of the question, we will start from the same initial state, but instead of impulse, okay, from the initial state, okay, a continuous horizontal force F starts acting on M2. So instead of giving it a sharp impulse, what we are doing is we are continuously applying a horizontal force F on the second block now. So in this case, again, we have to find out that what will be the maximum compression, and this time we'll find out what is the maximum acceleration of M1, this block. Okay, so we can do various things, including application of work energy in center of mass frame, or we can apply dynamics in center of mass frame, or we can even reduce it to a simple harmonic motion question once we apply the dynamical equation in center of mass frame and use the shortcut formula for simple harmonic motion in this kind of situation, reduced mass concept and all that. So we have to not only solve this problem, but we have to develop an approach where this type of situation we can do with minimum calculation and No, minimum analysis. Yes, that is reduced mass, right, Ganesh? Yeah, correct. Very good. Okay, so let me start with the normal mechanics way of solving this. Then we'll come to SHM kind of method. Okay, so this is at natural length initially. This is at rest, but this has just about started moving with the velocity v naught because g is equal to m1 v naught like this. Okay, so you can see that this system has a linear momentum of m1 v naught and has a mechanical energy of half m1 v naught square. Okay, so this is just after t equal to 0. So after some time now, if my system has reached this situation where the momentum of A has carried it forward, but it has also pushed the spring against B. So B has also got pushed a little. However, A's momentum is more than B's, so the spring is in a process of compressing. So this has become L minus X now. And as a result of the push that B has got, this has got a velocity V1, V2. Whereas as a result of the push in the backward direction that A has got, or the first one has got, this is V1 which has become less than V1. So now at this time, you can see the momentum of the system has become m1 v1 plus m2 v2, and the energy of the system has become half m1 v1 square plus half m2 v2 square plus half k square. So this will always hold true. This equation 1 and this equation 2 will always hold true. Okay, so it is that standard type of problem where now you can see that initially v1 is greater than v2, so x is increasing. The compression of the spring is increasing because m1 is approaching m2, but v1 is reducing with time, v2 is increasing with time. So at some stage v1 becomes equal to v2, after which v1 becomes less than v2. So then x is again decreasing. So at that point of time, M2 starts separating from M1. So the spring starts relaxing. Okay, whereas here the spring was compressing. Okay, so it is precisely this moment in between when V1 is equal to V2, that is when X is maximum. So in these two fundamental equations, if we substitute condition for X to be maximum, is that the relative velocity between them is 0. So that means V1 is equal to V2. So that's how we answer the first part. Okay. So V1 is equal to V2 equal to VCM at that time, which is M1 upon M1 plus M2 times V0. And therefore, half M1 V0 square is equal to half M1 plus M2 into VCM square plus half Kx maximum square. So when we substitute this, we will get our value of Kx maximum from this. Where this mu is reduced mass. Okay, that's one thing. And the other thing is we can also see that when V2 is maximum, that is basically when the spring is back to natural length. Okay. So what is happening is that the spring is first compressed. Okay, so when the spring is in a compressed state, it is pushing V. Okay, then spring reaches maximum compression, then comes back to natural length. So when it's at natural length, there's nothing happening. But next moment, the spring has actually extended. So the moment the spring is extended, it's now pulling back V. Okay, so at this point of time, V2 starts decreasing, whereas at this point of time, V2 was increasing. So at this instant, V2 has reached maximum value. Okay. So you can see that B speed, the second block speed reaches the maximum value when the spring is back to natural length. So that is when it's like a perfectly elastic collision has completed between M1 and M2. So M1 V0 is equal to M1 V1 plus M2 V2, but half M1 V0 square is equal to half M1 V1 square plus half M2 V2 square. This is the condition for X to be 0, so V2 to be maximum. So if you now see these two equations, this is the equation of head-on perfectly elastic collision. So you'll also realize that V2 minus V1 is equal to V0. Okay, and M1 V0 is equal to M1 V1 plus M2. So from this you will see that V2 will become M1 minus M2 upon M1 plus M2. Sorry, 2M1 upon M1 plus M2. This is the maximum value of. Okay. So I'm not solving these two equations now because I know how to solve them already. They are this thing only. The way to solve them was that, just subtract the equations. And compare them that way, just like we've done that for the derivation of 1D elastic collision. Like that, the solution will come. Yeah, second question, may we are applying constant force. Okay. But I will also explain the first question with the shortcut method first. Okay, so I'll come back to the second question. But I will explain the first question by this SHM method now, which will give me a very fast way of verifying my answer. Okay. Okay, now, so this is the fundamental method of solving the question. Okay. So this was part 1 by fundamentals. Now let's see it by SHM method. So this is like, I know in the back of my mind that this system is going to do SHM about the center of mass, because we know this system will be in SHM in the center of mass frame, not in the ground frame, but in the center of mass frame. Okay. So what we do here is we get into the center of mass frame ourselves. Okay. So in the ground frame, if we are seeing, then this is what is happening initially. Okay. This is moving at V0. This is at rest, and x0 is equal to 0. This M1, this M2. So we can see in the ground frame, okay, VCM is equal to M1 V0 upon M1 plus M2. Okay. Now let us say we get into the center of mass frame. So that's a very interesting way of doing this problem. So now we are here. We are traveling at VCM. Okay. So we are in the center of mass frame. So what we will see now, we will see in our frame, this block has a velocity, let's say u1, and this block has a velocity u2, where u1 is actually really, it is the velocity of block m1 with respect to center of mass. So it is v0 minus bcm. So it is v0 minus m1 upon m1 plus m2 bcm. v0 rather. So it is m2 upon m1 plus m2 v0. Okay. And similarly, u2 is velocity of m2 with respect to center of mass. So it is 0 in ground frame minus v0. So it is really, with the algebraic sign, it is times v0. Okay. So this is in the center of mass frame. So these are relative to C1. Okay. And we can see that this is 0. So this is in which phase of SHM? So M1 and M2 are at their respective mean positions. With respect to center of mass of SHM. Understand now? So with respect to the center of mass, what I will see is that M1 is having a range of motion like this. Okay, and M2 is having a range of motion like this. Okay. And this is when they were at mean position. Okay, so I know that they will do SHM with omega equal to square root of k by mu. Okay, या आदित्य U2 कैसे है देखो, ग्राउंड फ्रेम में M2 रेस्ट पे है ना, और सेंटर ऑफ मास का वेलोसिटी प्लस v नॉट है, सो रिलेटिव वेलोसिटी कितना हो गया, 0 माइनस v नॉट. ना. Okay, now see, I know that with respect to center of mass, okay, so just I'll come back to this. Okay, so with respect to my center of mass frame, what is happening, the block M1 is doing an SHM like this, back and forth like this. This is M1's SHM with an amplitude of A1. This is the mean position. So this is when its speed is maximum, and this is when its speed is 0. And similarly, I know that simultaneously M2 is doing an SHM like this. This is its mean position. This is when M2 is at rest. No, so they are going, they are going like this with respect to center of mass. Okay. So this is the position when the spring will have maximum compression. This will be L minus X max. Okay. When they are both at this extreme. So in fact, this is where they have started from. Okay, so the SHM has started from the mean position, okay, such that when they were both at the mean position, their speeds were maximum, and this distance was L. What the point now? So with respect to center of mass, they are doing this back and forth like this. So in fact, at t equal to 0, with respect to center of mass, they are both at their mean position of SHM. Okay, but this distance is L between them. Now what will happen at quarter of time period? They will both have come to one amplitude closer. Okay, and that is when the compression is maximum. So what is that maximum compression? That is equal to the sum of the amplitudes. This is the situation at t equal to 1/4 of the time period of SHM, whereas this was the situation at t equal to 0. So this diagram is clear now. From 0 to quarter of the time period. So now we have to just use this fact that, see, this thing that we've got now, this U1 is the maximum speed of A's SHM or M1's SHM. So therefore U1 that we have got, which was M2 upon M1 plus M2 B naught. Okay, this is A1 omega of M1's SHM. Okay, and U2 magnitude wise, which we got as M2 upon M1 plus M2. Sorry, M1 upon M1 plus M2. This one is A2 omega. This is equal to A2 omega. Okay, this is the maximum speed of M2's SHM with respect to C1. Okay. So that's it. Now from this you can see we've got A1, it is U1 by omega, and from this we've got A2, which is U2 by omega. So the maximum compression of the spring is A1 plus A2, that is equal to 1 by omega into U1 plus U2. So that is 1 by omega into M1, or rather M2. Now U1 plus U2 you will see is V naught only. So that's pretty obvious actually when you write this down. Is the relative velocity, that way also you can see. So obviously that has to be V naught. So it is nothing but 1 by omega into V naught. And that is nothing but square root of mu by K. Because omega square was K by mu, where mu is M1 M2 upon M1 plus M2. So this whole thing is an SHM derivation. But we can apply that directly in this question instead of using work energy and instead of making things so lengthy in work energy. Okay. Now, likewise, we can find the maximum velocity of B also. Okay. So at a numerical level, this problem becomes very simple then. All you have to do is you have to understand that when you got into the center of mass frame, the blocks were moving towards the center of mass with certain velocities U1 and U2, and the spring was at natural length. So that means they were at the mean position of the SHMs. So whatever velocities the blocks had with respect to center of mass at the initial moment, they are nothing but A1 omega and A2 omega of the SHMs. So from that we are getting A1 and A2, and the sum of A1 plus A2 is nothing but the net amplitude for the spring's SHM, and that is nothing but the maximum compression or the maximum extension. So it's almost like a formula based question now. Okay. Now for the second part, I'm going to use this approach first, and then I will come back to the fundamental approach. Okay. Because for the second part, you will see particularly the fundamental approach is more tricky. So second part, I will calculate first by SHM method. That is by examining SHM of M1 and M2 in the center of mass frame. Okay, but mind you, in this case, the center of mass frame becomes a non-inertial frame because the center of mass is accelerated. Okay, so that makes this question doubly more interesting. Whether we solve by fundamentals or we solve by SHM method. So anyhow, so x naught is equal to 0. This one is at rest, this one is at rest. Okay. And a force like this starts acting on the block. So this is what we are seeing in ground frame, in inertial ground frame. So we see the center of mass of the system, according to this guy, is F upon m1 plus m2. Okay. Now from here, let's get into the center of mass frame. So what is the person in center of mass frame seeing? Let's understand that. So just make a bit of a magnified diagram of this. This is at t equal to 0. Now this is also at t equal to 0. Now we are in the center of mass frame. So we become a non-inertial observer. We are traveling with acceleration ACM. So what we notice is that x0 is 0 at t equal to 0. Okay. But this block is experiencing a combination of two forces, F and pseudo force. And this block is experiencing pseudo force. Okay. So in the center of mass frame, this guy is having an acceleration A1. This guy is having an acceleration A2. So A1 is equal to ACM, that is acceleration of m1 with respect to center of mass at t equal to 0, when the extension of the spring was 0. Okay. And this A2 will become F minus m2 ACM divided by m2. So you'll see that it will become F minus m2 upon m1 plus m2 F divided by m2. So this will become m1 by m2 F upon m1 plus m2. Whereas this one is F upon m1 plus m2. But remember, this is relative acceleration. Okay, these two, they are relative to CO, these accelerations. Okay. So now, after some time, how this system is going to look in the center of mass frame. Okay. This is moved by some x1. This is moved by some x2. The length of the spring has become L plus x. So along with pseudo force, there is also now additionally spring force, kx, kx. Okay. So we know that these two will be doing SHM in center of mass frame such that m1 x1 is equal to m2 x2. x1 plus x2 is the net extension of the spring x and the omega square of the SHM. So x1 will be some a1, okay, into 1 minus cos omega t type function, and x2 will be some a2 into 1 minus cos omega t type function, where omega will again be square root of k by reduced mass. Okay. So you can see that this x1 ranges from 0 to 2a1 and x2 ranges from 0 to 2a2. So correspondingly x, which is x1 plus x2, this ranges between 0 to 2 times a1 plus a2. Okay. So the spring itself has an equation like this type of SHM, because this is that secondary type of SHM where there is constant force acting. Okay. So basically I can see that for X maximum, I have to find this now. This is what I have to find. Okay. So now coming back to the initial picture. Okay, at the initial picture, they were at which part of the SHM? They were at extreme position of SHM, because X is 0 now. So X equal to 0 or X1 is 0, X2 is 0 is the extreme part of SHM. Now the two blocks are doing SHM, which is now like this. If you look at X1 as a function of time, it's this type of thing. It's not, it is from 0 to 2a. So this is mean. Okay, and these are extreme. Similarly, X2 is also this type of SHM now. Okay. So X1 equal to 0 is the extreme position of SHM. Okay. So at this point, the acceleration should be a1 omega square, and X2 equal to 0 is the extreme position of that one's SHM. So that's the shortcut trick. Okay. So whatever acceleration that block has, that should be equal to a2 into omega square. So if you look at the FBD of M1 and M2 with respect to center of mass at t equal to 0, they are both at extreme of SHM. Okay. So once again, in that FBD which I had made earlier, okay, at t equal to 0, what was that FBD like? This had F and pseudo force, and this had only pseudo force. So this had an acceleration a1. So this a1 was only with how much? Capital A1 omega square. And this had an acceleration a2, and that was only how much? Capital A2 into omega square. Okay. So if you remember, we had calculated this a1 was F upon m1 plus m2, and that is only a1 into k by mu. And this a2 was m2 by m1, was it? No, m1 by m2, sorry. Into F upon m1 plus m2. And that only is equal to a2 into k by mu. Okay. So you can see that from this, I'll get a1 as mu f upon m1 plus m2. So that is m1 m2 upon m1 plus m2 whole square into f. And from this, I'll get a2 as m1 by m2 into f upon m1 plus m2. Okay. There's a k also somewhere here. Yeah. Yeah, Aditya, I'll go over the second question again. So this will become how much? This will become m1 square upon m1 plus m2 whole square f by k. Okay, this will be my A2. Okay, whereas my A1 was this much. So the maximum compression of the spring is A1 plus A2. So let's work that out now. Okay. So in that we can take 1 upon M1 plus M2 whole square into F by K common, and we have M1 M2 plus M1 square. So we can see that this becomes a maximum compression. Okay. So I'm just taking you to the beginning of this once more. If you're not clear how we have applied the SHM concept, I will just briefly take you through the additional concept of SHM, that is SHM with a constant force acting also once. Okay, so to understand this, let's first talk about the secondary type of SHM. That is, if we have an SHM like this, where this is initially like this. Now at t equal to 0, this block is also at rest, x0 is also 0, but we start applying a force F like this. Okay, so then what is x as a function of time? Okay, x is not a sine omega t, x becomes a into 1 minus cos omega t, where that amplitude becomes f by k and omega becomes square root k by m. Is this obvious to all of you, or it takes some time to analyze this? Okay. This is obvious, no? It should be obvious. यहाँ पे the block never comes back to negative side of x. Its displacement varies between 0 and a certain maximum value, and that maximum value is 2a. Okay. So x maximum is 2f by k. So a is half of x maximum. Okay. So how we understand this, let's see. So in general, at some point of time when this is L plus X, the equation is like this: F minus Kx is equal to Ma, or d2x by dt square is minus K by Mx, okay, plus F by M. So it is the equation of the type d2x by dt square is minus omega square x plus some constant. Okay, so the solution of this differential equation versus the standard one, this one. Now for this, what should happen? For this, Kx should be equal to Ma, where A should be equal to minus d2x by dt square. This should correspond to an FBD like this. When the displacement is x, there's only Kx acting. There is no secondary force F acting. So that is the standard SHM. That's this one. So this one's equation is A sine omega t plus phi. But this one's equation, how it becomes like this, let's see. So the solution of this is x is equal to some constant plus some amplitude into sine omega t plus phi. Okay. You see, only this kind of an equation satisfies this. So let's write this constant as something else. We should not confuse with initial value of x. So let's say this constant is something else, like beta or something. Okay. So this is this type of a solution. Now we can see x's initial value is beta plus a sine phi, and that should be 0. And dx by dt, that is v, is equal to a omega cos phi. So v naught should be a omega cos phi. So v naught should be a omega cos phi, and that is also 0 because the block had started from rest. So from this we can see that phi must be equal to plus minus pi by 2. Okay, and from this beta plus minus a should be equal to 0. That means beta should be equal to a, and phi should be equal to minus pi by 2. So that's how we know that x should be equal to of the type a plus a sine omega t minus pi by 2. So that becomes a into 1 minus cos omega t. This is how we know this. The solution of this equation with the condition that initial x was 0 and initial velocity was 0, it gives this, which corresponds to this graph. Where x is varying between 0 and 2a. Okay, so this also gives us that x naught is 0, v naught is 0, but also acceleration initially is a omega square. So this is the concept that we are applying in that question now. Both the blocks separately. Okay. So coming back to our question over there, in addition to this, of course, you have to apply center of mass concept to understand how the SHM is happening. So let me explain the SHM in the center of mass frame. So with respect to our center of mass frame, which is a non-inertial frame, traveling with a constant acceleration, which we saw is F upon m1 plus m2 earlier. Okay. So in this frame, if we look at the two blocks, at t equal to 0, they are at rest. Okay. The spring is at natural length. Okay. So the only forces acting on them are the two pseudo forces and this external force F. So at t equal to 0, the acceleration of this block with respect to center of mass is like this, and the acceleration of this one with respect to center of mass is like this. Okay. So now if you look at the same situation after some time at t equal to t, so by now this block has moved by x1 and this block has moved by x2. So the spring has got an extension of x1 plus x2. So at this point of time, what all forces are acting on this? F, the two pseudo forces, but in addition to that, there is also spring force. So kx and kx. Okay. But remember, we are in the center of mass frame. Okay. So with respect to center of mass, what will happen is that m1 x1 will be equal to m2 x2. Because in the center of mass frame, the center of mass should not displace. We are in that frame where center of mass is a fixed point, and with respect to that frame, the two bodies have moved by x1 in one direction, x2 in the opposite direction. So in the center of mass frame, delta x cm should be 0. So that is telling me this. Okay. And x1 plus x2 is equal to the net extension of the spring. That is the constraint relation. So from these, we can now see that x1 will be m2 upon m1 plus m2 x, and x2 will be m1 upon m1 plus m2 x. So these two equations we are going to make use of. Okay. Now from the free body diagram of each of these blocks, how we can get the SHM condition, let's see that next. So from this one's FBD, we can see that if I say it's having an acceleration in this direction, this one is having an acceleration in this direction at time t. Okay. m1 ACM minus kx is equal to m1 a1. Okay. So this is m1 upon m1 plus m2 f minus kx. Now from here, x can be written as m1 plus m2 upon m2 into x1. Is equal to m1 d2 x1 by dt square. So you can see now that d2 x1 by dt square is equal to minus omega square x1 plus some constant c1, let's say. Is that type of equation where omega square you can see is k by mu, and that c1 you can see is f upon m1 plus m2. Okay. Now similarly, if you look at this one's FBD at t equal to t, you will see f minus m2 ACM minus kx is equal to m2 A2. Okay. So now you can see in this whole thing is actually a constant. So again some constant minus kx, where again x we will replace in terms of x2. So this will also become an SHM equation. So we'll substitute that here. So this equation will also become of this type. Some constant minus omega square x2 is equal to d2 x2 by dt square. So both the SHMs are going to have the same omega when you compare. Okay, so omega square here will also be k by mu. Okay, and for both of them, so that means my x1 is also of the type some beta 1 plus a1 sine omega t plus 5. and this x2 is also of the type some beta 2 plus a2 sine omega t plus phi. Okay. Now x1's initial value is also 0 and v1's initial value is also 0. So that will give me that thing that beta 1 is equal to a1 and phi is equal to minus pi by 2. Ditto same over here. So from that I know that this x1 will be some amplitude a1 into 1 minus cos omega t, and this one will be some amplitude a2 again into 1 minus cos omega t. Now Aditya, is clear how we got the SHM equations. So from that I know that the net extension of the spring, that will also be some amplitude into 1 minus cos omega t, where that amplitude is equal to a1 plus a2. Okay. Now also we can see at the initial moment at t equal to 0, m1 is at x1 equal to 0, v1 equal to 0, and a1 equal to a1 omega square state of its SHM. Okay, state or phase you can say. Okay, that is the extreme position. So whatever acceleration we calculated from FBD, that is now giving us a1. So from this we can calculate how much a1 is. And ditto same for m2. So a2 at t equal to 0, whatever value we calculated, that gives us capital A2. So that becomes the simplest way of finding out the maximum extension of the spring, which is capital A1 plus capital A2. So it's like, we have to approach this question with that prior knowledge. Okay, that then we can do it in the shortest possible way. So for example, I'll just take a numerical example. Suppose I had this block of 6 kg mass attached with a spring to another 3 kg block, and the spring is, let's say, 20 Newton per centimeter, and this was the situation. Okay. And we start applying a force of, let's say, 5 newtons. And I ask you find maximum extension of the spring. So the thing is, you have to understand that this is doing that SHM in the center of mass field. With respect to center of mass, you have to understand that this is doing that SHM. Okay. Where with time, this will move like this. With time, this will move like this. Where this will be like this, and this will be like this. Okay. So in the center of mass frame, initially, whatever acceleration this is having, a1 at t equal to 0, let's say a1 naught, okay, and whatever acceleration this one is having, this is nothing but a2 omega square, and this is nothing but a1 omega square. Okay. So now you can see from this that acceleration of center of mass is 5 by 9 meters per second square. So this will be experiencing a pseudo force only at t equal to 0. And this one will be experiencing a combination of pseudo force and the external force. So directly from this FBD only, without doing any other calculation, you can see that A1's initial value, that is capital A1 omega square, is going to be nothing but the pseudo force divided by mass. So capital A1 omega square is nothing but ACM, which is F upon M1 plus M2. Okay. So now you can see here that from this, omega square is K by mu, and mu is 2 kg. Okay. K was this much Newton per meter. So omega square is 2000 divided by 2. So 10 raised by 3 radians per second whole square. Okay. So from this we can see that A1 into 10 raised by 3 is equal to F upon M1 plus M2, which was 5 by 9. So A1 is 5 by 9 into 10 raised by minus 3 meters, or 5 by 9 millimeters. Okay. Now the other thing we can see is that M1A1 will be equal to M2A2. So we don't even need to make the FBD of the other one. So A2 is going to be M1 upon M2 times A1. So M1 upon M2 times A1 is how much? It is 2. So it's going to be 2A1. So A2 will be 10 by 9 millimeters. So now from this we can directly see that maximum extension is going to be how much? 5 by 9 plus 10 by 9. So 15 by 9 or 5 by 3 millimeters. So this should be the maximum extension. So you can see minimum number of steps. We can actually find this maximum extension by just this much. But that is if you're aware from before what this system is doing. It's doing this type of SHM. Understood now? You just think of the center of mass like a wall, you know, and from both sides two springs are attached. But this constant force acting on this one is actually the pseudo force, and the constant force acting on this one is F minus pseudo force. Okay. Okay. Now by the same method, how will we find the maximum acceleration of the block M1? Now remember, we are applying the force on M2. So here also we have to be very clever. Okay. M1, M2. Now with respect to center of mass, let's say this acceleration is like this. This acceleration is like this in the center of mass frame, which itself is going like this. Okay. So you can see that in the ground frame, okay, acceleration of block 1 is going to be A1's vector sum with ACM, because this is relative. Okay. So it's basically when this block goes to the other extreme to a distance of 2A1 like this, with respect to center of mass, it is having an acceleration like this of A1 omega square. So that point of time, so this acceleration of M1's maximum value will become A1 omega square plus ACM. Yes. Where we already found out A1, A2 and all this now, just now. So A1 omega square we just saw is actually F upon M1 plus M2. Okay. And that is the same thing as ACM. So in ground frame, the maximum acceleration of M1 will be equal to 2 times F upon M1 plus M2. Okay, so this is that SHM related concept. So even if you're doing this question by fundamentals, you will actually either have to solve the dynamics like we did to prove the SHM a little while back, or you will have to do something even more complicated, which is solve work energy equation in the non-inertial frame, where you'll have to consider work done by pseudo force to find the maximum extension, because the maximum extension will occur when the kinetic energy of the system is zero with respect to the center of mass frame. So that will also be an option for you, but it's going to be lengthy. Okay, so the easier option, and in any case, you have to know the SHM concept of this kind of system, no? Because you can be asked the time period, the time it takes for the spring to go from zero to maximum extension, then to maximum compression. So you have to know the whole SHM part of this. So that is why this becomes essential by this method. Okay. All right. Now next, one of the things I wanted to do today is questions related to impulse momentum. Okay, and in that we will include the concept of angular impulse also. So I have this kind of a system next. So I have a rotating pulley with a ladder attached on one side. So this is a massless thread, but this is a rotating pulley with moment of inertia I and radius r. Now this one here, this is a ladder of mass, let's say 20 kilograms, and length equal to, let's say, 5 meters, so about 15 feet. And there's a person standing at the bottom of the ladder. Let's say it's a small boy or something, so size is less. Okay. So the person has a mass of, let us say, 40 kgs. Okay. And on the other side, we have a counterweight. So we have a balancing weight. So obviously its mass is going to be the combined mass of these two. It's going to be 60 kg. It's given to us that this moment of inertia is 30 kg meters square, and the radius itself is 1 meter. So it's quite a large pulley. Okay, like this. Okay. Now initially the system is at rest. Okay. Now the man starts climbing the ladder very slowly at a uniform speed. So if he reaches the top after 100 seconds, you want to find angular speed of the pulley and speed of the block with respect to ground. While the person was climbing. Okay. So we will see that we can do this type of question by applying fundamental impulse momentum type of concept also, or by applying a special conservation kind of principle also. Okay. So let's see how all that can be done. Just try to work this out. Okay, Nishita, I'll just verify your answer. Nishit, I'll just show why, but I'm getting the value of angular speed as 0.013 radians per second, or basically 4 by 3 into 10 raised power minus 2 radians per second. And similarly, I'm getting the speed of the block in the ground frame to be 4 by 3 centimeters per second. Anybody else got the answer? Please let me know. Okay, so we will take a look at this question by two approaches. One is the impulse momentum concept. Okay. So in the impulse momentum concept, what's going to happen is that everything was at rest initially. So in order to start climbing the ladder, the person has to gain some momentum in the upward direction. So he has to generate that momentum by applying a downward impulse on the ladder. There's obviously normal reaction acting between him and the ladder, but okay, so J is the downward impulse or push by the person on the ladder to generate an upward momentum. So as a result of that, what happens is that the ladder is jerked downwards. So the string also ends up applying an impulse. Let's say J1 like this, which acts on this. And because it's a rough surface of the pulley, that impulse is different on the other side. But massless string, so same impulse acts on this block. So as a result of these impulses, what happens is that the person develops an upward velocity, let's say V1. The ladder starts to come down at V2. This starts to rotate at omega. And because of thread length conservation, this will also have an upward velocity of V2. So on the person, if you look at his free body diagram, and we apply impulse momentum, you will see J is equal to mass of the person into V1. So J is equal to 40 V1 because his mass was 40 kg. Okay. If you look at the ladder, now on the ladder there is a downward impulse J, and there is the thread is applying an impulse J1, and the ladder is developing a downward velocity V2. So the net downward impulse is J minus J1, and that is mass of the ladder into V2. So we have J minus J1 is 20 into V2. That's our second equation. Now next up, if you look at the pulley, then the only impulse that is acting, which is creating angular impulse, are these J1 and J2s, okay, which is creating a clockwise angular impulse, sorry, anti-clockwise angular impulse. So on the pulley, we have J1 minus J2 into R, anti-clockwise, is I omega, is anti-clockwise. So we have J1 minus J2 is equal to I by R into omega. Okay. So that's our third equation. And finally, if you look at the block on the other side, there is J2 acting and it's giving it an upward velocity V2. So on the counterweight, we have the equation J2 is equal to M2 V2. So J2 is equal to 60 V2. This is our fourth equation. Okay. Now also the thread is not slipping. So no slipping condition for the thread. So you have V2 is equal to R omega. Okay. Because the thread is coming down over here with the speed V2, going up over here with the speed V2, and is rotating with omega. So V2 must be equal to R omega. That's the constraint relation. Okay, so next, if we substitute all this in these equations, you can see that we can convert this equation to J1 minus J2 is equal to I by R square into V2. Okay. Then J minus J1 is 20 V2 and J2 is equal to 60 V2. So this will become actually 30 V2 when you substitute the values. Yeah, V1 and V2 are in the ground frame. So V1 plus V2 will become the relative velocity. So from that you can calculate the time taken to climb the ladder. Understood? So now just add these three equations. So you are having J is equal to 20 plus 30 is 50 plus 60. That's 110 V2. Okay. Now compare this with the first equation. Okay. So J is equal to 40 V1 is equal to 110 V2. So this tells us the relation that V1 is to V2 is equal to 11 is to 4. Okay. Now the rest is from the kinematics information. Okay. The person climbs the ladder. Ladder's length was 5 meters. In time, 100 seconds. So that means the relative velocity of the person is 5 meters by 100 seconds or 5 centimeters per second. So a relative velocity kitna? It is V1 plus V2. Because the ladder is coming down at V2 and the person is going up at V1. So with respect to the ladder, the person's net velocity is V1 plus V2. Got it now? So now connecting this equation and this equation, we can see that V1 is 11 by 15 times V relative. So it is 11 by 3 centimeters per second. V2 is 4 by 15 into V relative. So V2 comes out to be 4 by 3 centimeters per second. And omega is V2 by R. So that's 4 by 3 into 10 raised to minus 2 radians per second. Okay, so hope this concept is clear. Now we can apply a conservation principle here, and that conservation principle would be something like this. Now, at the time when the person applies an impulse on the ladder applies an equal and opposite impulse on him. Then this all acts. These are all internal impulses. Okay. But because of this, there is some external impulse that acts through the center of the pulley. Okay. So about the center of the pulley, okay, angular impulse is 0. So angular momentum of the system about the center C of the pulley is conserved. You can apply this concept directly. No, Aditya, we can't really calculate this by center of mass displacement because position of center of mass is not conserved by anything over here. Now you can see there's external impulse acting now on the system. So the center of mass of the system will actually go up as the person is climbing. You can see 60 kg on the other side is going up. Then 40 kg person on this side is going up and only 20 kg is coming down. So center of mass is having some net displacement. So this can either be done by the impulse momentum method that we discussed or by this second method that I'm showing you, which is conservation of angular momentum. Now initially, what is the angular momentum? It was 0 because everything was at rest. So final angular momentum also has to be 0. In the final state, this guy is going down at V1. This ladder is coming down at V2. This block is going up at V2. And this starts rotating at omega. So this is how much the person's mass, let's say M1, into V1 into R, linear momentum, moment arm, R cross MB, that formula. This concept, okay. So linear momentum into moment arm. So you can see that it's like this. Okay, so that's why it's like this. Okay. Oh, sorry, the person is going up. My mistake. So we should have clockwise angular momentum. Clockwise. Okay. So if I have written clockwise as positive, then the ladder's angular momentum is negative. the Pulley's angular momentum is negative, and the counterbalance on the other side, its angular momentum is also anti-clockwise, so it's negative. So this total angular momentum should be 0 because the initial angular momentum was 0. Okay, so from this you can see you will get that relation that M1 V1 will come out to be mass of the ladder plus I by R. Sorry, mass of the ladder into V2 plus I by R into omega plus M2 V2. And then you put the constraint relation that V2 is equal to R omega. So you will get this constraint relation that M1 V1 is equal to mass of the ladder plus mass of the counterbalance plus I by R square into V2. So you get that relation. And then use the relative motion concept. Understood, na? Okay. Okay, so this is one of the unusual applications of conservation of angular momentum, which we'll see. So we'll conclude here in today's lecture. Next time we will pick up more such questions which have combination of concepts of conservation principles along with constraint relation and all this. Okay, so that's it for today's session, people. Wish you all the best.